Okay, so in this problem, we're gonna go ahead and try to make this target product right here using only the given starting blocks in this little set of 5 molecules right there. Okay, so the first thing I always do when I try to do a synthesis problem is I try to think about how I'm going to start tackling it, right? I also try to think of what came from what, essentially, right? I have this benzene ring. Okay, at least 3 of my things have a benzene ring in there. I have this pretty big group over here, right? And then this smaller, NO2 group. This almost definitely came from some sort of nitration, right? But then this group looks a little bit more scary, right? It looks a bit more complicated. But it looks like its origins are in something that looks like this. And then you have the benzene ring over here, this entire area right here. So this isn't as scary to add on, right? Because how do I add this sort of a group onto a benzene? Well, we can use the Friedel-Crafts acylation, right? Friedel-Crafts acylation. I hope I spelled that right. That'd be pretty embarrassing if it's going on YouTube spelled wrong. Friedel-Crafts acylation, right? And so the thing that we're going to add, I'm just going to draw this literally flipped upside down because it's just easier to see. Cl, and then I would have to use, in this case, a chlorine, right? I'd have to have a chlorine here before I add it. So that's going to be one of my goals. It's going to be to make this thing right here. I want to make that thing eventually so I can add it to that benzene ring. Okay, so let's not jump too ahead of ourselves. So let's figure out where that benzene ring is coming from. Well, I have 3 options here. I have 1, 2, 3. This one looks the most, appealing because, oh, look, I have a carbonyl. This one gives me a carbonyl. That saves me some work, right? Yeah, I can see why you would think that, but then you also have this H group right here. That H group is going to be very hard. H group, I guess H group, hydrogen group is going to be very, very hard to swap for this entire huge group. So that's not looking too appealing to me. Then I have this OH group, which doesn't look appealing at all because that OH is honestly just a bother to me. I might as well not have that, aka over here. I might as well not have that so I can have almost a fresh start, if that makes sense. So I'm going to go with just a good old simple benzene right there. Okay. So say I have that benzene. That looks like this right here. Benzene. I'm going to have to either add this group or this group. Okay. Since they're both going to be electron withdrawing groups and they're both going to direct meta, right? And in this case, I need them to direct meta because if I add this group first, I'm going to have to add the next group in the meta position. If I add this group first, I'm going to have to add the next group in the meta position. So that doesn't really change anything. So I'm going to add whichever one I think is easier to add. And I think this one's definitely right now just easier to add. So I might as well get that product ready for myself for when I use it, for when I need to use it later. And the way we nitrate is we use nitric oxide, so nitric acid, HNO3, and we use H2SO4. And that's going to give us this molecule. Also, for these problems, I don't care about, whether I show the mechanism or not. That would just take way too long. This already takes quite a bit. So we have this thing ready over here. This thing is ready to go. Okay, so that thing's ready to go. Now the question is, how do I add a group right here or right here? This is symmetrical, so it doesn't really matter. So how do I add that? Well, I got to prepare this, right? I have to prepare this so I can add that in. So the first thing I'm going to do is I'm going to start off with what are our starting materials. And in this case, it's pretty easy. This is really the only one I can start off with, or this theoretically, but this one obviously looks like it's going to take longer because then I would have to add this group and all that. Okay, so I'm going to start off with this right there. Go ahead and erase that. That aldehyde. So if I have that aldehyde right here, H, how can I get myself on the road to getting this Cl in place of where that H is? I don't know of any mechanisms that can do that straight away. So the first thing I'm going to do is I'm going to make this into a carboxylic acid. I want this. And the best way to do that is to use this reagent with H2SO4 and H2O. Okay. That's going to give us this carboxylic acid. Now, to turn this carboxylic acid into this molecule right here, that shouldn't be too big of a problem. Okay. Also, this chlorine if you're wondering why this chlorine isn't there, we'll take care of that later. That's a pretty simple alpha halogenation, which is a really simple reaction, and we'll do that at the end. So I need to get this Cl from this OH. So what are the reagents required for that? And this is a pretty common one you'll find in any organic chemistry class, SOCl2, along with just a aprotic solvent, CH2Cl2. Okay, that'll give us this molecule right here. Now we're ready to add this to that benzene ring that we made earlier, right? So let me just highlight this actually. I have a highlighter, I might as well use that. So we have our two connecting pieces. This is going to be this part right here. And this is going to be this part right here. This Cl is not there yet. And then these are quite annoying looking, although they're in fact really, really easy, and we'll take care of those soon. So we have these two right here. So let's go ahead and combine them now. If I want to do a Friedelscraft acylation, I'm going to start off with this, the thing that I already made previously, so it's ready to go, NO2. I'm going to react it with the molecule of choice that I want to add. It's going to be this, Cl. And then I have to use the solvent that's actually going to pull this Cl off of this, right? I need that Cl to come off so I can form a carbocation, which one of my double bonds in this benzene ring will then attack, right? So how do I pull that off? I have to have the correct solvent. Oops, I'm just erasing everything. Cl, and the correct solvent is AlCl3. Also, this could have been a bromine, and then I would just use AlBr3, but in this case, I use Cl. It really doesn't matter that much. Okay, so now I actually made the product I was hoping for. NO2 is still there. Then I added in the meta position right here. I added this group. So it's starting to kind of take shape. Let me zoom out a little bit. It's starting to kind of take shape. I have this going on. This double bonded oxygen you could have imagined being right here, and we still haven't added those two ester groups yet. Okay, so now before I add that ester group, I want to take care of this pesky little chlorine that I have on this carbon right here. Okay, that's actually a really, really simple mechanism, so I'm just going to do it right now. What you would do is you would use Cl2 and acetic acid. Okay, so that's the two things that make this, acetic acid and Cl2. Acetic acid is, of course, the solvent. So what that does is it adds to that alpha carbon, so you still have that. We still have this. I'm drawing it a little funky in terms of its actual structure, just because it makes it easier to see. So we have this group right here. This is the alpha carbon. That's where we add the Cl. And that's looking perfect. We're basically done. I mean, I'll go ahead and number the carbons just so it's easier to see, but we have, that color's not showing anywhere. Let's do, I don't know, let's go with a blue maybe. We have the number 1 carbon, number 2 carbon, number 3 carbon, just so we're on track. 1, 2, and 3. And that chlorine is attached to the 2 carbons, so far so good, okay? Now for the interesting part. Now I really got to start adding some esters, right? And we can use 2 mechanisms that we've already learned, which includes the alcohol version of the esters we want to add. So these are O and ethyl groups. Those come from ethanol, right? Which looks like this, OH, right? And that H is going to be deprotonated. I'm not going to go over the mechanism, but the first thing that's going to happen is we're going to add this is going to happen. Then if we do one more round of that, I could have technically just, gone straight to the answer, but I kind of want to show you what's really happening. If I do one more round of this, plus some acid, you always gotta have some acid in there, H2SO4, plus some acid, I'm gonna get this final product. You have this NO2 over here, you have OET, these are both esters right here. And then I'm going to have that ethyl group coming off of it with a chlorine on that second carbon. And now it looks like we have our final product. So yeah, this isn't too tough of a synthesis. It takes a few steps, but each step hopefully should make a little bit of sense, and as long as you do a couple things, as long as you plan out the problem intelligently, you think of things like meta directing and ortho and para directing, and you also count your carbons, realize how many do I have to add, where are they coming from, what does it look like, and then don't let things like this scare you. I know whenever I first saw this problem, I was like, god damn it, I have two esters attached to a carbon. That's going to be kind of annoying to make. But then I realized, remember that whole hemiketols and hemiacetals and all that kind of stuff? That's exactly what this is. It's just a full acetylation. Okay? So yeah, that's how you do this problem. And thanks for watching, guys.